In this episode of Remote Calculus, we will be doing an example of implicit differentiation. We have a cardioid here, and we're going to be finding the slope at various points on the curve. Implicit differentiation is about finding instantaneous slope, but you have the variables blended together rather than having the formula solved explicitly for one specific variable. When you're working with implicit differentiation, you do need to recognize that the two variables are functions of each other. Usually we let y be the dependent variable and x be the independent variable. And so we want to remember that y, for our example, is a function of x. Y is f of x. So I'm going to actually replace the y's at the beginning with f of x so that we remember that. Our formula then was x squared plus y squared, but I'm replacing y with f of x. And then the other side had the quantity 3x squared plus 2y squared minus x squared. But again, remember y is f of x. So when we go to work the next line, we'll replace the y with f of x. Okay, so all the same derivative rules apply. We haven't changed any derivative rules. We just need to keep remembering that y is a function of x. So on the left side, the derivative of x squared is 2x, and the derivative of this term will be 2 times f of x to the first power, but then the chain rule says multiply by the derivative of the inside function. Then on this side, the derivative of this whole expression starts off with the chain rule idea of taking the derivative of the outside, so 2 times, and then you leave the inside of the function alone. But again, I'm replacing y with f of x. And then our new power is 1 because we did the power rule. Now the chain rule says we need to multiply by the derivative of the inside. So the derivative of 3x squared is 6x, and then we're going to get 4 times f of x to the first power, but then the chain rule says multiply by the derivative of that inside function. And then the derivative of x is 1. Okay, so we're done applying the rules of derivatives. Now we need to clean it up and solve for f prime. At this point, I think I will go back and replace the f of x's with the letter y because it'll look cleaner, but I'm going to leave f prime of x written as f prime because that's what we're trying to solve for, okay? So I get 2x plus 2y f prime of x equals 6x squared plus 4y squared minus 2x, and then I'm not doing anything to this term at the moment except for the f of x I will rewrite as y. Okay, still trying to clean it up. I need to distribute over here. So 6x squared times 6x will become 36x cubed. And then 6x squared times this term will become 24x squared y f prime of x. And then 6x squared times minus 1 will be 6x squared. Moving on to the next term, 4y squared times 6x will be 24xy squared. 4y squared times this term will become 16y cubed f prime of x. And then 4y squared times minus 1 is negative 4y squared. And then negative 2x times 6x is negative 12x squared. And then negative 2y times this term will be negative 8xy f prime of x. And then negative 2x times negative 1 is positive 2x. All right. So all of this is still equal to what we have over on the left side. Notice that there is a 2x on this side and a 2x on that side. So if I subtracted 2x from both sides, there would no longer be a 2x. So why don't we get rid of that, because we have a long enough expression. I'm also going to circle all of the terms that have f prime in it. So notice all of these terms have an f prime. And any term with f prime needs to be on one side, and any terms that do not need to be on the other side, because you're trying to solve for f prime, so you're trying to isolate it. I'm going to choose to put all the f primes on the right side and all the terms that do not have f prime on the, well, I guess I said that backwards, didn't I? I'm going to put all the terms with f prime on the left and all the terms that do not have it on the right. All right, so we already have 2y f prime of x. And then I'm going to move the 24x squared y f prime of x. And then I'm going to move the 16y cubed f prime of x. And then I'm going to move the negative 8xy, careful because you're adding to get rid of it. So on this side it'll show up as an addition. And that's all of them. Okay. So then on this side, I'm left with 36x cubed minus 6x squared plus 24xy squared minus 4y squared minus 12x squared. And those are all our terms. Apologize my handwriting. I'm kind of writing around the camera so that I can kind of see what the camera is doing. So I'm not in my normal stance. Okay, the whole point of moving things was to get terms that have f prime in every one of the terms so that you could factor it out. So factoring out the f prime, I get 2y minus 24x squared y minus 16y cubed plus 8xy. And on this side, we still have our same terms. And now that I factored out that f prime, we are down to our last step. F prime of x will equal all of these terms as a numerator divided by the factor that I created over here. So numerator will now be 36x cubed minus 6x squared plus 24xy squared minus 4y squared minus 12x squared, and all of that will be divided by 2y squared minus 24x squared y minus 16y cubed plus 8xy. Okay, so we have accomplished finding a formula that will give us the slope at any point on our cardioid curve. I picked out a few points for us to specifically look at. So we will find the slope at those points, and we'll also find the tangent lines. By the way, all of this work will be posted as photos on the end of the video so that you can spend a little more time looking at it. I guess before we leave this page, I would probably combine any like terms. There really aren't any like terms aside from the negative 6x squared and the negative 12x squared. So the numerator can become 36x cubed minus 18x squared plus 24xy squared minus 4y squared all over 2y minus 24x squared y minus 16y cubed plus 8xy. And if you're plugging numbers in, it'll be better to plug it into the cleaned up formula. That's an example of what I've been saying earlier, that cleaning up, you'll see the benefit of it as you start to use your derivatives. So it was beneficial, I think, to clean that up. Okay, so we have the points here of 0, 0.5, 0.6, 0.314, 0.5, negative 0.4653. This point was kind of easy to see right on the graph. I chose 0.6 and 0.5 as some nice x values to work with. At the very end, I'll show you how we got these y values. They are rounded, but they're close enough for our practical purposes. Okay, so those are the points we're going to try to find the slopes and the tangent lines. And okay, so we're going to need our formula for our derivative, which we have handy here. So f prime of x, again, in its cleaned up form, was 36x cubed minus 18x squared plus 24xy minus 4y squared. And the denominator was 2y minus 24x squared y minus 16y cubed plus 8xy. And we have the points, so like the first point was 0.5, and the formula will give us the slope at that point as long as we plug in the coordinates of the point. This is a nice easy one to plug in, because the 0 for x is going to make every one of these terms 0 except for that one. So we'll have 4 times 0.5 squared. And then the denominator, I'll have 2 times 0.5, but that term will be 0. And then we'll have 16 times 0.5 cubed. And then that term will be 0. And let's see, in the numerator here, 0.5 squared is 0.25. 0.25 times 4 is 1, so we get negative 1. 2 times a half is 1. 0.5 cubed is an eighth. And 16 times 1/8 is 2, so I get 1 minus 2. And so that gives me negative 1 over negative 1 for a slope of 1. All right, so at the point 0.5, our slope is 1. Now at the point 0.6.314, it's a little bit messier. So we have 36, the x is 0.6, and I will plug 0.6 everywhere there's an x. And then the y is 0.314. And then in the denominator, I give 2 times 0.314. And then x is still 0.6. Y is 0.314. X is squared on that term. Y is cubed on this term. And there we go. There are x and y all plugged in. Now I think I figured this out a little bit earlier, and if you correctly number crunch that, you should get a slope of negative 2.16325, and you can round it somewhere if you would like, but I'll leave it there for exactness. Okay, then nothing changes in terms of the idea for our last point. 0.5 is the x, and negative 0.4635 is the y. And again, if you plug 0.5 in for the x, I'm following my numerator up here, and the y is negative 0.4635. Don't forget the negative. And don't forget any squares and the cube in the bottom. Minus 24 times 0.5 squared times negative 0.4635 minus 16 times negative 0.4635 cubed plus 8 times 0.5 times negative 0.4635. Okay, and again, if you number crunch that correctly, you should get a slope of 1.07 So 1.07457. And that is the slope at that point. Okay, so those are the slopes. Again, slope is rate of change. So anytime that we are interested in our rates of change, we might be using them to interpret something, or we might want to find tangent lines. So we're going to use our slopes to find tangent lines. Again, our points were the ones listed here. We've already found the slopes. The first line we will find is for the point 0.5, negative 0.4653. At this point, you can find the equation of your lines however your favorite strategy is. I like the strategy of recognizing that you have a point. We want the line to go through this point, so y on the line has to be negative 0.4653 when x is 0.5, and the slope is 1.07457. And so y equals mx plus b. That allows me to solve for the b. So negative 0.4653 then is going to have that amount subtracted from it. And that will give us our b. And if you correctly do that number crunching, you end up getting b equal to negative, almost negative 1, negative 1.002585. So the line that's tangent to the curve at that point is y equals 1.07457x minus 1.002585. And that's the tangent line at that point. Now, it might be good for you to practice finding the other two tangent lines. At the end of the video, there is a graphic that shows all three lines in the equations. And that is a fairly solid example of implicit differentiation, as well as some review as finding tangent lines. Have a good rest of your day.